A very good day. My name is Tan Hong. I'm from UTHM, University Tun Hussein, Malaysia. In the context of the military and the TVET law enforcement training, the shooting accuracy is more than just a skill. It's a core competency that directly influences the combat areas and the public safety. To align with the goal of the TVET 4.0, I am proud to present the project. It's namely AI Smart Shooting Scoring System, and the project ID is KVN968. The evolution is still largely depend on the manual inspection of the paper target or the semi-automated method. This approach are labor-intensive, slow, and susceptible to the human error. Even though the manual method is offer the flexibility but lack of the speed, the semi-auto method is offer the speed but lack of the robustness. Although they are advanced electronic systems such as the sensor-based scoring technology have introduced to improve the accuracy, but they require specialized hardware, complex installation like height maintenance costs which are not user-friendly. But they are also good news. The recent advance in the artificial intelligence like AI and the computer vision CV, particularly the deep learning-based object detection, enable the accurate real-time analysis of the visual data. The YOLO only one family is especially suitable for this application due to high detection speed and the computational accuracy. When combined with a high resolution wireless camera, the computer vision will offer a practical alternative for the automated evolution. This is our research methodology project. The phase 1 is the research and the flexibility study. We identify the YOLO V5 as the optimal model for balancing the speed and the accuracy. This is because of the early version of the YOLO V1 to the YOLO V4, it struggled with the small or the overly big object such as the builder. So until the version YOLO V5, we introduced the Arco box, multi-star feature pyramid connection, and the scalable model size. These enhancements allow the YOLO V5 to achieve an effective balance between the speed and the accuracy. Next, underlies the fast API to manage the asynchronous RTSP stream. The system will function as both a live detection and a forensic product to ensure the real-time performance on the high resolution wireless camera is to 1516 pixels. Then we come to the phase 2, it's the pre-processing phase. The data sets were collected under different lighting conditions, distance, and the builder head. And they labeled via the labeling. Where is the we manually draw a box around the builder and the targets. To ensure the stability, a 30-frame calibration buffer calculates a mention homography matrix blocking the perspective. Then the data is split into 70% training, 15% testing, and 15% validation. The accommodations such as the rotation and the scaling applied to the enhanced model generation. Then we come to the phase 3. It's the model training phase. The model underlies the transfer learning with the pre-trained week to detect two classes. Class 0 is the target, class 1 is the builder host. Hyperparameter were optimized to distinguish the small scale impact from the complex background to ensuring the neural network maintain a high precision with the high definition video fix. Then we come to the phase 4. It's the post-processing. The live modes, our main modes, is meant to coordinate to Pacific block and risk with 4.0 times digital zoom and the string-based radar analytics. And our subsystem is the forensic modes. We employ a open CV counter detection in polygon testing for the surgical precision. The results are integrated into a cumulative section tool for the automated performance analysis. Alright, thanks for watching the demonstration. I hope you love it. So right now we talk about the global impact. First of all, we achieve the SDG 4 is the quality education in the TVET environment. The efficiency is the key. Our system transforms the shooting range into a data-driven classroom, allowing the instructor to focus on mentally rather than the manual scoring. Next, we achieve the SDG 9. It's called the industry and the innovation. By localizing the AI technology, we eliminate the need for expensive important sensor hardware. We are proving that high precision defense tech can be built affordably right here in Malaysia using the nothing more than a standard camera. Most importantly, we address the SDG3 and the SDG12. We're removing the need for the personnel to manually check the target downrange. We ensure the several training environment. We also reduce the technical waste by maximize the continuity of the existing high resolution wireless controller. Now let's talk about the number. The biggest barrier to enter for the professional shooting training is the cost. On the left hand side, you can see the industry standard, the system from the SIUS or the Menton, because they rely on the expensive, specialized, and fragile hardware like the S-passing sensor and the dedicated routine monitor. Singly, will set a TBET sender back between $5,000 and $15,000. This is simply unsustainable for the mass automation. Now we look on the right hand side, this is our solution. Our hardware start is illegally simple. We can use our own laptop around 2,000 Malaysian ringgit and a high resolution wireless camera around 100 ringgit. Our total hardware cost is minimum 2,100 Malaysian ringgit. So how do we do it? We don't need expensive sensor because we replace them with computer vision logics. We use AI to see the builder hole and the target. We eliminating the tens of thousands in hardware complexity. This verdict is clear. Our system delivers a 19% more cost reduction. We are not just creating a product, we are democratizing professionally training by shifting the cost.